Hi, everybody. For this series, I'm going to talk about the lab EL218. That's the time domain simulation of electrical circuits. Well, since you're familiar with LT Spice, and this one I'm going to move forward. We're going to analyze analog and digital circuits. We will start with the analog circuit first, and that's the will followed by digital circuits. That's in our series 2. Let's take a look at RC circuits or RC series circuits. You have our R resistor connected to a capacitor in series, as well as the power supply VS in series. This one is the first order circuit. You already know about it. You have background. And we will consider the transient response. We're looking for the voltage drop across the capacitor and the current flowing through our capacitor, or VC and IC. By applying KVL, you know that the voltage, the source voltage, going to be equal to the voltage drop across resistor plus the voltage drop across capacitor. For C, you know that the current flowing through the capacitor, that's the time dependent, equal to C derivative of sorry, the voltage drop across the capacitor at arbitrary time. That's the derivative with respect with t or time. Then UVR is going to be equal to IR, right? By Ohm's law. And UI simply IC, because this is the series circuit. And for your IC, that's equal to C derivative of the voltage drop across a capacitor with respect to t. Finally, you're going to end up with Vs equal to RC, the first derivative of voltage drop across the capacitor with respect to t plus Vc t, or the first order differential equation. Now we are going to solve for Vc of t. You rearrange the term and you do integration. This is just the simple math, so I'm not going to go through this. And finally, you're going to end up with this term, exponential negative t over RC equal to Vc, voltage drop across a capacitor, minus Vs, that's the source voltage, divided Vc at the time t equal to 0 minus Vs, that's the supply voltage. And you rearrange the term, you end up with Vct, that's the time dependent, equal to Vs plus the Vc at t equal to 0 minus Vs, exponential negative t over Rc. There's some interesting here. Well, for special case, at the beginning, if you still have open switch, you have no supply voltage for a capacitor, so the voltage drop across capacitor is 0, correct? And then this term drop, you end up with Vc of t equal to Vs minus Vs exponential negative t over Rc. And you simplify the equation, you end up with Vs of 1 minus exponential negative t over Rc. And you know that your Rc, the product, that is the time constant in the unit of a second. Same as your Ic, you can look for Ic by applying C, the first derivative of Vc of t with respect to t. And you end up with Ict equal to Vs over R exponential negative t divided by Rc. Let's take a look at the voltage drop across the capacitor at arbitrary time. At the start, t equals 0, so this term become 1, right? And your VC becomes 0 at t equals 0 because 1 plus 1, sorry, 1 minus 1 is 0. When the time passes by, uh, this term drop or getting smaller and smaller. So you end up with finally it's going to reach a stable uh, condition, or VC is going to be stable, which is equal to Vs because this term drop are very small. And finally, you can see the plot between VC and the time. So this is the time domain. At the beginning, this is the voltage drop across the capacitor. At the beginning, at t equals 0, of course, the voltage drop across the capacitor equal to 0, and still start charging up your capacitor until it reach your maximum voltage of Vs, which is equal to the supply voltage. And for UR, you take a look at the VR, the voltage drop across resistor. You have this equation, and then you end up with VR of t equal to Vs exponential negative t over Rc, or Rc equal to tau, where tau is the time constant in the unit of per second. And this is the relation between VR, or the voltage drop across resistor, with t in seconds. You take a look at the equation, you know that at the t equal to 0 at the starting point, this becomes 1, right? Exponential negative is 0. So your VR start from Vs, or equal to the supply voltage. And then when the time passes by, this term starting drop, and then in the form of an exponential term. Okay, so this is about the first step of the lab that we're going to work on. Now for LT Spice, let's take a look at the setup. This is your circuit. You have R equal to 10K and you C equal to 0.1 microfarad. By hand calculation, you know time constant tau equal to RC. So you have a 10K multiplied by 0.1 microfarad. And you end up with your time, or time constant, equal to 1 millisecond. And the time constant actually tell you, how fast the capacitor will be charged or discharged. And at the time equal to time constant, you want to consider, because you have to take the number into your table of the lab. When t equal to tau, you have this term become exponential negative 1, and your VC become 63.1, 631.63 millivolt, or it's about 63.1% of your maximum voltage in the term of the voltage drop across capacitor. Now for RT Spice, take a look at the power setup. You might consider we will go through RT Spice. Okay, actually I can do it now, right? And then let's go to RT Spice, and I have the circuit. That's the RC circuit, just right here. Okay, let's minimize. And then, oops, too big. Sorry, do it again. Just do it. Okay. This is pulse. Okay, this is what you need to set up for the pulse input as the supply voltage. You go to component 2 and you pick up voltage. That's the way you do it. Left click to place, right click to stop. And you right click, you go to advanced, and you click on pulse. Here, this one you have to fill it up. What is V initial? V initial is mean that you start from 0. Okay, so I have everything right here. And V on in the unit of volt, you can say this is the amplitude, become 1 volt. And T delay is mean just like you have switch. You might delay before you close the switch or you have the complete circuit. I put this one as 1 millisecond. What about T rise? T rise is mean that the LT spine not allow you to put T rise equal to 0. It has to be, sometime. So we put this one as, really very small. The T rise mean the time to take from the voltage start from 0 to reach the maximum voltage. In this case, is 1 volt. So I put, the time rise become 1 nanosecond. At the time fall, at this point, you put the same number. That's the 1 nanoseconds, very, very small number. And T on become 1. So this is the time interval become 1 second. Now for transient analysis, because you need to do the time domain analysis, you need to choose the transient analysis, or you go to edit, let's cancel this one, and you go to bits by analysis, you pick up uh, transient analysis, ask you for the stop time. So I put this one as 10 milliseconds because your T on actually is just one, wait a minute. That, let's see, where is T on? Host. And this is your T on, the last one. Okay, after T4. So I put this one as 1 second. But I do the stop time to be 10 millisecond. That's good now. Okay, so let's take a look at your LT space. You have everything in here. So what you're looking for is what? Sorry for the background noise. Um, this is what you have to take the number down. We already calculate for the time constant or tau, and they ask you about the voltage drop across the capacitor and T equal to tau. Hold on a second, I'll close my window because it's so noisy here. Okay, let's continue. Oh, still noisy, sorry. Okay, getting much better. Then you want to find the voltage drop across capacitor at T equal to tau, or the time constant. And we already calculate for that. So you might want to compare the one that, let's see, just right here, rate. The voltage drop across capacitor at T equal to tau, that's the 631.63 millivolt. If you compare this number to the number that you get from our LT spice. Okay, so the time constant equal to 1 millisecond. Uh, T equal to 1 millisecond. Now you do simulation, run. Um, Is it error? What happened? Less than two connections to node NC01. This node is used by V2. Let me close this one first. Circuit. I close this one. Just not get confused. Oh, okay, because I did this one. So I need to queue this guy and do a simulation again. Now everything is okay. Well, you can see that for the x-axis, that's the time interval. I go up to 10 milliseconds. Now you go to icon and you want to see the voltage drop across the capacitor, right? And from circuit, that's the node B. So VB, that's what we're looking for here. The voltage drop across the capacitor. At the beginning, because you have the time delay, right? Before you close the switch for 1 millisecond, you can put this one as no time delay to be 0, second. That's okay. And that's mean the capacitor start charging up. For the time pass by, it will reach the maximum voltage. That's equal to the supply voltage, 1 volt. So this is behavior of your capacitor in RC series circuit. You can also take a look at the pulse. If you want to plot, you go to plot setting, you go to add trace, and the supply voltage or the pulse uh, at the node A. So you click on A. You can see this is your pulse input supply voltage. Now you want to look for the voltage drop across capacitor when t equal to tau or t equal to time constant. The time constant is the 1 millisecond, right? But you have delay for 1 millisecond, so you need to take a look at the time equal to 2 milliseconds. To do that, you go to get cursor. You left click on VB, and you have cursor right here, and you put your cursor over the dot line and move until you get a horizontal. This one to be 2 milliseconds, and you can do the reading for the voltage drop across capacitor at t equal to time constant. So I try to get as close as possible. So you have this one as 2 millisecond, and I have the vertical reading. That means the voltage drop across the capacitor become 632 millivolt. Okay, that's very close. Also, they ask you to look for what? The current flowing through resistor at t equal to time constant. What you can do, you can also add another plot of the current flowing through resistor R1. You click OK, and the red line is the current flowing through resistor R1. So this is about okay, because it's the cursor active on the green line, so you want to click on IR1, left click, so you locate your current. That's become a 36.72 microamp. Okay, so this is about the first order circuit. Now let's move to the second circuit. This one is RLC series circuit. This means you add another inductor in series with L and R, and this becomes the second order circuit. By applying KVL, UVS, the supply voltage, Of course, going to equal to the voltage drop across resistor plus the voltage drop across inductor plus the voltage drop across capacitor, VC. And they all have the same current because this is the series circuit. IC equal to IL equal to IR. And your IC simply equal to a C derivative of the voltage drop across the capacitor with respect to T. And also VL, you know that equal to L dic by dt. Then you work on math. Vs is going to be equal to this one. And if your Vs equal to 0, your solution, we see this is the second order differential equation. We see equal to A exponential st. And you plug in Vc in this equation. Your Vs is going to be equal to this. For Vs, does the supply voltage equal to 0, or you just take away your supply voltage. You end up with this equation, and you can solve for S, which has become this one, this term. You can see that S have like two roots, or two solutions, because you have plus and minus sign here. So if A exponential S1t become the solution of VCT, as well as the B exponential S2t, also the solution for VCT by superposition, you can add them together is to become the solution of VCT, right? Where S1, actually edit is wrong. S1 is supposed to be negative R over 2L. R over 2L missing here. And this one should be plus, and this one should be minus. Sorry about that. Now consider about when R, the first term, in the square root, over 2L squared is greater than 1 over LC. That's give you the real number, right? And that's give you two roots. In this case, it become over-damped. And also, if R over 2L, I did a lot of, yes, I did something wrong. Actually, I should put square root here. Sorry. Just take a look at this term then. If R over 2L square less than 1 over LC, and that's mean you have complex numbers, right? This is less than 0, the result. You have two complex roots. In this case, it's become underdamped. And the last one, if two terms are equal, let's give you 0. So you end up with R over 2L or negative R over 2L, one root. And that's real number. In this case, it's critically damped. Okay? So that's about our analog circuit. Now we're going to move on to digital circuit. In part 2, let's see, I have someone here at my lecture. Where's that? Hold on a second. Well, doesn't matter. Let's get it through. Let's over it again. That's the merge one. Okay, let's move to digital circuit. Part number 2 of the lab EL218. Well, let's recall for basic digital gates. You have OR gate. And this is the expression for OR gate A plus B. You have two input OR gate, and C is your output. Since you have two inputs, the total combinations become 2 to the power of the number of inputs. In this case, 2. So you have 2 to the power of 2, or 2 to the second. That's equal to 4. So you have 4 combinations. And for OR gate, you know that if one input is 1 or high and 0 is low, um, if you have one input become 1, your output is going to be 1. Now we'll move to AND gate. This is expression A, B. That's for NAND gate, AND gate, sorry. In this case, it's going to give you output 1 if only both inputs are 1. Okay. The last one is the exclusive OR gate. This is the expression. It's going to have output to be 1 if two inputs are different. 0, 1, either 0, 1 or 1, 0. Otherwise, it's going to give you output to be 0. Okay. Um, yeah, that's the basic digital logic gate. Now take a look at LT space. Um, this is the circuit that we are going to work on. We have our 3 inputs, A, B, and C in. And that means you have total 2 to the power of 3, or to the cube, 2 to the cube, right? Because you have 3 inputs. So you have a total 8 combinations. Well, for your input C in, you can see your period. If each digital logic is uh, stay for 5 microseconds, that means for one period, it's going to take what? How long? 5 multiplied by 8, right? So that's the 40 microsecond. So that's why I put the period to be 40. And V on is going to be half of your period because that's include high and low, or 0 and 1. So you see in your period become 40 microsecond. And B, your period become half over your C in. As we're asked for input A, your period become half over the input B. Okay? And this is for the symbol. You probably wondering what is the circle here it means. Well, that means the inverted output. For output, this is your, if you take this one as the output, it simply become an OR gate. But if you take this one as the output, this is going to be NOR gate. N stand for not. So that's invert your output. This is your circuit. And you can also write expression, for each gates. For A1, I put this now. This is exclusive OR. So you have two inputs, A and B. So A exclusive, B exclusive OR. What about A2? Same, exclusive OR. And A3, you pick up what? Inverted output. This is your A3, right? I did something wrong here. Sorry, A3. You have input C in, and you have another input A1. So C in and A1. All of them have to be a complement or inverted output, because you take this one, the output from the circle here. A4, you have two inputs, A and B, and you complement because you take inverted output to be your input for A5. Now go to your LT space. I already have a digital circuit. Okay, just to save time. Now take a look at your input A. Refer to the table of the left node. Just go to the table. Okay, here. So this is your input A, B, and C. A become a 0, 0, 1, 1, 0, 0, 1, 1. Okay. Let's take a look at my lecture better. All right. Starting from input C in first. Okay, you have 0, 0, 0, 1, 1, 1, 1. So this is your C in. That's why I have what does it mean? When you go to components, okay, and you select voltage, look like this. You right click, you go to advanced, and you choose repose. For C in, you know that the period become 40. So this is your period that you need to put it in. Okay, what is 0? 0 is mean that the voltage start from 0. That's the V initial. 1, what is 1? That's mean V on, or the maximum voltage, or the amplitude of the pulse. You don't need time delay, so your delay becomes 0. T rise, 1 nanosecond, very small. Same as the T fall, 1 nanosecond, very small. What about 20? 20 is the T on the logic 1 lasts for 20 seconds, microseconds, sorry. And you also have a T off or digital 0. Digital logic is 0, right? That's another 20 microseconds. So you have period become a double of 20 or 40 microseconds. Okay? Now you can work out by yourself for input what? This is input B, right? And this one for input A. And you can do a simulation. You have everything just right here. And for mode of analysis, you go to transient, right? Because this is time domain analysis. You just put in a number. Why I have a 50. This is microfarad. Sorry, microseconds, right? The maximum period is 40 microseconds. But this one is that I'm not really put a U as the microsecond. So I just put like 40 seconds. It doesn't matter. And I just want to cover, everything. This is the maximum period. Is the time interval is 40 seconds. So I just simply put 50 seconds. That's enough for the x-axis. I click OK. Now you're ready to run. Simulate. Oh, sorry, I have error again. That's because I put this one. So I need to kill this guy. Remove it. Let's just show that for example. And then let's do a simulation. Okay, you already have a plot. The blank won't show up. This is the time you set up from 0 to 50 seconds. Since you have 3 inputs, and you ask you to take the number down on your table, which are what? You go to the lab here, the output D and output E. So you need 5 plots. You go to LT space, you go to plot settings, and you add plot plane. You already have 2, but we're looking for 5. So you add another 3. 1, 2, 3. So we have what? 1, 2, 3, 4, 5. Okay. If you want to start with the input A, according to this one, A, B, and C. You want to start with A. So you need to add trace for A, right? So we already labeled on the circuit PA. So you click OK. So this take T on to be 5 seconds, and the amplitude become 1 volt. It start from 0 to 1 volt. Next one, okay, you locate your mouse, your cursor on the plane that you want to plot. This one going to be what? B, correct? The next one, this period is going to be double of input A. And for input C is going to, the period is going to be a double of input what? B. So you go to the plot, you go to VCAN. This is your 3 inputs of that. Now are you looking for output D? You go to trace, and this is your output D. Oops. Oh, what happened? A, B, C, I did something wrong. Sorry. Maybe I put this one in the wrong plane. Sorry. Oops. Oh, what happened? Um, anyway, doesn't matter. Let's start over again. Do simulation, and then I add another full plane. 1, 2. I just want to do something quick. 1, 2, 3, 4. I need one more. Okay, I have 5 planes. The first one going to be what? Input A. Okay. The second one is what? Input B. The third one is the input C in. Okay. And this one is become our output D. You already have D. And then the last one is what? That's the output C. E. Sorry. E. Okay. You have everything just right here. Now, if you want to take a number to put in on your table, let's see. Let's pick up 0, 1, 1, and you're looking for output D and output E. 0, 1, 1. What you can do is that you can go to the plot. Where is 0, 1, 1? You look for A, 0, B is 1. This 0, 1, 1. Okay, that's word. 0, 1, 1. And you can see your VD become 1. Digital logic, and your E, digital logic, become 1 as well. Okay, and you can do the rest of your reading. You can even pick up your cursor here, so you can move around to do the reading. So this one active on VA, right? You see the dot line, the rectangular. So this means that the cursor active on VA only. And you know that your V equal to 1 volt, or the logic is 1. And if you move this one to 0, it shows you a 0. That means that digital logic is 0. That's all about it. How to work on digital circuits using LT Spice. Okay.